Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to describe what happens when you hook an inductor here to an AC sinusoidally varying voltage source. So we have an inductor L, and to write the equations you have to know how to write the voltage across an inductor. So I wrote it a couple different ways. The voltage across an inductor is equal to L times delta I over delta T. Or in the language of calculus, the voltage is equal to L di dt. And I'm going to go ahead and use this here because it's required for the mathematics of solving the equations. So if we go ahead and write a current loop here, what we're going to have is V max sine omega t minus L di dt equals 0. And again, if you haven't had any experience with calculus, just bear with me for just 1 or 2 minutes, and then the rest of the video will be completely relevant. So this can be solved for the current by separating the variables here. So what we can do here is we want to solve this for di. So if we do that, what we're going to have on the other side, let's see here, is L times V max sine omega t dt, I'm pretty sure. Oh, whoops, no, that L would be in the bottom. My bad. All right, so again, all I did here is I put this term on the right, divided by L, multiplied by dt, we'd get this term right here. All right, now this is solved by integration or anti-differentiation. So the current here is going to equal, now this is a constant, and the antiderivative of sine omega t is minus cosine omega t over omega. So this thing has an antiderivative of, let's see, minus V max over omega L cosine omega t. If you give me a moment here, I just want to be sure this is right. I want to differentiate it and make sure I get this. So we differentiate cosine, we get minus sine times omega. The minuses will cancel. This omega will cancel that, leaving me with this. Yep, that's right. Okay. So again, that's the only calculus step that we need for this video. The rest of this is very relevant for anyone watching this. So you'll notice here we have I equals V over something. An important thing to realize is that something right there has to have units of ohms, and it does. And you've probably already watched my video on capacitors, right? This is a similar type of thing. This has units of ohms. This is called a reactance. In this case, it's called the inductive reactance. So I would call it X sub L equal to omega L. Again, you'll notice it's frequency dependent, just like the capacitor's reactance was. However, here it's a little bit different. In this case, high frequency means high reactance, which would mean low current, whereas with the capacitor, high frequency had the opposite results. See if I can, physically argue why this says here. So if the frequency is really high, that means this is going from plus minus to minus plus to plus minus really, really, really fast. The voltage waveform's always changing. And what that means is it's always trying to change the current direction. The current's going back and forth at high frequency. And inductance, remember, is resistance to changes in current, right? If the current's changing all of the time, that gives you a high, relatively high voltage across the inductor, and the inductor's fighting the input voltage, right? Remember, inductance is analogous to mass. Mass is resistance to changes in velocity. Inductance is resistance to changes in current. High frequency means we're changing current all the time, so the inductor's fighting the circuit a lot. Really low frequency, in fact, imagine this being basically a DC source. What would happen is, for a DC source, the voltage across this would basically go to 0. You'd have really, really, really high currents. In fact, you'd have to have a resistor in here or it would be shorted out, and the currents would be overall really, really, really high. So inductive reactance, inductance is resistance to changes in current. That means that your reactance is really high at high frequencies because the currents, the input voltage is always trying to change the current. All right. Next important thing here is to compare this minus cosine omega t with the input wave, the sine function here. So I'm going to go ahead and let's see, where am I going to do that? I guess I'll do this right here. I'm going to do just like I did last time in my last video here. And what I'm going to do is sketch a graph of sine omega t. I'm going to do it right here. Boom. At about 0. Okay. All right, x, y. Sine x looks like this, basically. Again, where this would be like pi, 2 pi, 3 pi. Now, I'm going to go ahead and color code these here. Cosine, remember cosine wave starts here, ends up here, it's a peak here, 0, a peak. So your cosine wave looks like this. But that's not what we want, right? This is minus cosine. So minus cosine would flip that upside down. So I'm going to get rid of these dots even. So that means it goes through here, and it's a 0 here, and it's a maximum here. Here, let's see, max 0. Okay, so minus cosine x. Whoops, oh, I can do better than that. It's looking something like this. All right. Not the best graphs I've ever drawn, but y equals minus cosine x, and then the black one was y equals sine x. Pretty rough sketches, but good enough. The very important thing here is this minus cosine x needs to be shifted to the left. Actually, let me think about what I want to do here. I want to compare this minus cosine x. I want to write it in terms of sine x. Okay, so this sine wave needs to be shifted to the right to turn it into a minus cosine wave. So that means that sine of x minus pi over 2 is equal to minus cosine x. And again, if I had a better sketch, it might be a little more evident, but take the black curve, it needs to go right by pi over 2 to turn it into the green curve. That means that sine of x minus pi over 2, that would give us a shift right. Remember how horizontal shifts work. And then we would equal minus cosine x. So what that means over here is that the current can be written, right, V max over omega L, and then minus cosine omega t can be written sine of omega t minus pi over 2. And very important to compare this to the input voltage. And you notice this minus pi over 2. So when we draw the current phasor for the inductor, the current phasor is lagging behind the input voltage. Right? So, why would that be? Well, let me talk about a mechanical analog to this. So imagine, I'll do this right here. Imagine a mass with a force. And for now, let's just imagine this force is constant except it changes direction. So half the time it's this way, half the time it's this way. When the force is in this direction, this mass is going to start moving to the right. When the force changes direction, at that instant it changes, the velocity is still to the right. It's going to take a little time for this thing to stop and then start going this way. Then when the force changes direction, this will slow down and start going this way. So you'll notice that the force will change direction before the velocity does. So in this case, we would say that the force is leading the velocity around. Well, it's kind of the same thing is happening here. The input voltage is driving currents in certain directions. The inductor has a resistance to changes in current, just like this object here has mass, which is resistance to changes in velocity. So when the current is in the following direction, right, then imagine that the voltage here changes to this polarity, plus minus. This polarity now is trying to push a clockwise current, but because we have an inductor here, it takes a little while for that current to change direction, right? Because that's what inductance is, resistance to changes in current. Then eventually the current does change direction, but then this changes voltage. right? And then it takes a little while for that current to change direction. So that's why the current phasor lags the voltage phasor. So really important things about the inductor. Really important thing number one is right here. The inductor has a reactance equal to omega L. This is effectively the resistance of these circuits. So I'm gonna, it has units of ohms, and when you have high reactance, that means low current. Low reactance, high current. It's frequency dependent. If I go to my mechanical analog here, imagine this. If this force was changing direction really fast, like 20 times a second, the average speed of this would be very small, because it would never have any time to pick up any speed. So a similar thing's happening over here. When the voltage is changing frequency really fast, the current never has time to grow to a larger value. So the average current's very, very low. And then the opposite thing happens. If the frequency is very low, think about my mechanical analog here, that means that the force will be in this direction for quite a while. So down the road, you'll end up with a reasonably high speed. And then the force changes direction and the thing slows down, but it does speed up again. So when this force reverses direction really, really fast, 10 times a second, 20 times a second, 50 times a second, the speed overall stays very low. Same thing's happening here. When this voltage changes from plus to plus minus really fast, that means this current never has time to grow. So important thing number one right there, the reactance equal to omega L. Very important thing number two, the current phasor lags the voltage phasor by pi over 2. That's going to be very important for my next video. So to kind of recap before I get to the next video, if you've watched my 3 videos on the resistor, the capacitor, and the inductor hooked to AC voltage sources, remember that for the resistor, the current was in phase with the input voltage. For the capacitor, the current led the input voltage, and for the inductor, the current lags the input voltage. That's going to be really important for my next video. Hope this helps. Have a great day.